Hello, I'm Mariana and I'm going to conduct a regression analysis based on medical costs personal dataset. Nowadays, medical insurance is a must in people's life. Given the high cost on medical bills, people tend more and more to get insured. Thanks to this and machine learning, our motivation for this project is to take advantage of big data to solve questions of our interest, such as which variables affect medical insurance bill costs and to predict costs given a set of values. First, we have our first model and our three null hypotheses to be tested. As we can see, these are the defined variables in our model, and we are going to talk about the hypothesis testing further on. Oh, here, female smokers southeast and northwest were set as dummy variables in order for us to understand our data better. Now we have our exploratory data analysis. Let's begin with a box plot for each of our non-dummy variables. We have age, which is very symmetric, and the median is around 39. Body mass index, which is really symmetric as well, but has a few upper outliers. Number of dependents, symmetric, and no outliers. Median around 1, and the charges, which have many upper outliers, and the median is around 10,000. Now we have our dummy variables against charges. Our first plot, sex versus charges, shows us insurance costs for females are less than for males, and that both variables have many outliers. Second, smokers, in, being a smoker increases medical insurance cost about $1,000. And now we can see how region of origin of the insured can affect the cost. As showed, the median is around the same value, so it goes down to how data is more concentrated around the median or which one is more symmetric. Here we have a brief summary of our data. We have the binary variables, which are the dummy ones, and the non-binary variables. Let's begin with our regression analysis. For purposes of hypothesis testing, we're going to conduct every hypothesis testing with this unrestricted model, which was the previous one. Now, this null hypothesis is to test whether our dummy variables have any effect on the model. Here in the restricted model, we drop them, and here we have our new model. We conducted a linear hypothesis test, giving us that the F statistic is around 673 and our 1% critical value is equal to 3, so we can reject the null hypothesis at any level of significance, meaning at least one of our dummy variables contribute or affect the cost. Then we have the second and the third hypothesis to test, which is to test if age and children have any marginal impact on charges. Given, again, our unrestricted model, we have the following output. Given our two-sided hypothesis, we have this t-value for age, and for children we have this t-value, meaning we reject our third and second null hypothesis at any conventional significance level. Our last findings mean if we want to estimate a better model, we need to include children and age. And as for the dummy variables, we need to see which of them are statistically significant and which ones can be dropped from our final regression model. We have here a few other observations. For example, if we were to set all of our variables to 0, our expected medical cost would be less than 0. As we can see here, our coefficients are negative. Our R squared is this one, which means we have a moderate fit and our Kn value is really, really high. We're going to see this other model, which has a logarithm on charges. We dropped all our non-statistically significant variables, and here we have another logarithm. As we can see, all our independent variables now are statistically significant at any level. Coefficients are more interesting to work with, and our R squared value is a moderate fit of the actual data and higher than the unrestricted one. and we found our lowest eigenvalue equal to this value. We made assumptions such as independence of residuals, normality, and homoscedasticity. To prove independence, we run a Darwin-Watson test with this as our null hypothesis. Our p-value was 0.43, so we failed to reject our null hypothesis, meaning residuals are independent. Here we have our plot of the autocorrelation function, and we can see, given all our lags are within the bounds, they don't have any significant effect, which means our residuals are independent. Normality is easy to see that residuals are not following a normally distributed distribution. Here to check homoscedasticity, we conducted an NCV test that states as null hypothesis that the variance is constant, but we encountered heteroscedasticity, which means the variance increases in the regression coefficients, making them hard to trust. As the conclusion is that by conducting different regression models, we encounter with different problems such as heteroscedasticity that made us realize predictions would be really far from reality, and that understanding how variables affect the cost can be very useful in creating a model that fits the actual data is a really hard task. Thank you.